So in this section, we're going to talk about horizontally launched projectiles, a quick review of that, and then move on into things that are not horizontally launched. So a quick reminder before we get started, we know that gravity does not affect the horizontal component, which means the horizontal component for a projectile is just going to keep going at a constant rate. And we know that horizontal velocity does not affect the rate at which gravity acts. It still falls at the same rate. But questions about what happens to projectiles that are not launched horizontally. Well, take a quick look at this again, a quick reminder. Here's a projectile. When it's launched, its horizontal velocity is 60, and that stays the same the entire time that it's flying. What does change is the vertical velocity. It's changing by 10 meters per second each second that it's in flight, losing 10 meters per second on the way up, gaining 10 meters per second on the way down. You might say, wait, does gravity change direction? No, gravity is always acting in this direction at 10 meters per second squared. It's always accelerating downward, both on the way up and the way down. But take a look at the sign of the values and you'll see it. So for non-horizontally launched projectiles, what's going to change? Well, we've seen these equations before. This is the initial horizontal velocity. I'm going to add a little sub-zero on this one. And this is the initial vertical velocity. Now, for horizontally launched projectiles, this term was missing. We didn't have to worry about it. But now that we actually have something that's being launched at an angle, it's going to have some initial vertical and some initial horizontal. Where these two equations come from? They come from this, but we make the assumption that for all practical purposes, we'll assume that there's no acceleration. This yellow doesn't show up very well in the horizontal direction. That's true for projectiles. It's not always true for all situations. You could have a rocket car, for example, that is accelerating horizontally as it falls. But we'll stay with this for now. So take a quick look sort of graphically what's happening here. We have something launched, and I'm showing the vertical over here and the horizontal over here. As it travels, the horizontal stays the same at every single point. But the vertical gets smaller till at the top there isn't any, and then it grows in the downward part. For all of these, this horizontal piece remains constant. Question is, how do we calculate the horizontal component and the vertical component at any given point? Well, the horizontal is easy. That's just whatever it started with. The vertical is going to change by 10 meters per second each second. So real quick reminder of this one, how do we calculate this? Well, if you've got the initial velocity that it's being thrown at, you can break that into its two components fairly easily. Doing that, you should recognize that the initial vertical is just going to be, if this is theta down here, and again, we could draw that over on the other side, maybe that would help. You should recognize, oh yeah, just using cosine of theta is going to equal the adjacent side over the hypotenuse, V0, or rearranging that, you can get the initial horizontal is equal to V0 times the cosine of theta. Likewise, this is V sub y initial over here or over here. You can use sine to get that one. Now, just a quick note, a quick reminder again, this actually doesn't change as it flies. So I really wouldn't have to have the sub-initial on that one. But now here's the question. How do these components change with time? Well, we already talked about this one doesn't change, but this one is going to change by g times t. And actually, I'm going to make this positive. We assume that gravity is usually negative 10 meters per second squared. And so you simply end up this. This is the initial vertical velocity. This is the initial horizontal velocity. And so the horizontal velocity at any given time is just equal to the initial. The vertical velocity at a given time is equal to the initial vertical velocity minus, well, or plus negative 10 times t. Quick thought problem, this is a conceptual one. At what point in its path does a non-horizontally launched projectile have its minimum speed? The answer is at the very top. Why? At the very top, it is only moving horizontally. It's not moving vertically. And at that point, it has the minimum speed. Unless you count where it hits the ground and completely stops. Now, there's something interesting going on here with those equations, and I want to spend a moment talking about it. This dotted line represents the path a projectile would follow if there was no gravity. Because of gravity, though, after the first second, it still falls 5 meters below that line. If you remember, 5 meters is how far a projectile falls if it's dropped from rest after 1 second as well. And after 2 seconds, it's going to fall 20 meters from that point. And after 3 seconds, 45 meters. Well, 20 meters is how far an object dropped from rest falls in 2 seconds. 45 meters is how far something dropped from rest falls in 3 seconds. So there's something interesting going on here. So how do we figure out these distances, the 5, 10, and 45? Well, it's just this equation here where we're going to plug in -10 for the acceleration due to gravity, and then you got t squared. And if you plug in 1, 2, and 3 into this, you'll get how far it's going to fall below that line, our delta x. This is as if it was dropped from rest. So let's do a little bit of math on this one. So let's take a look at it. Let's say it was launched at 50 meters per second, and I happen to make it so this angle here is 37 degrees. If I do that, then this side ends up being 30 meters per second, this side's 40 meters per second, just to make the numbers nice. So here's my question. Where would the green dots be? If there was no gravity, and this thing continued to move at 40 meters per second horizontally as it flew, and it continued to move at 30 meters per second upward. No gravity, so it's not changing. Hopefully you would agree with me that after 1 second, I'm going to make the origin here. Sorry, I should explain real quick. We always make the starting point the origin. And we're working in 2 dimensions, so I'm using x and y. Whoops, went the wrong way. I hope you would agree that the coordinates of this green ball right here should be 40 meters over, because it was traveling at 40 meters per second for 1 second. And it should be 30 meters up, because it was traveling at 30 meters per second in the vertical. And that's not changing, because we're doing this, the green dot is without gravity. How about after 2 seconds? Well, after 2 seconds, I'm hoping you would agree, it'd just be 2 times 40, 80. And vertically, 2 times this 30 again, which would give us 60. After 3 seconds, hopefully you discover that, it should be that. And I won't write it all down this time. But now, where will it be actually with gravity? I'm going to write the times next to this so you can sort of see it. It's 2 seconds, here's 3 seconds. Well, these numbers come from the equation we talked about before. So anyway, so far what we've done is just simply taken the initial horizontal velocity times time and the initial vertical velocity times time and multiplied by time, and that gave us these coordinates that we're talking about here. But now what happens if we involve gravity? Well, the change in the y position is just 1/2 times the acceleration of gravity times time squared. This is 1 second. And it's going to give us the 5 meters. And then for 2 seconds, we're going to do the same thing. And for 3 seconds, we get that, which gives us our 45. So now I can actually ask the question, what are the coordinates then of these red dots, since it's going to fall below that path that we had? Well, if you fall 5 meters below the coordinates 40, 30, where does that put you? It should put you at 40, 25. What have I changed here? Well, here's our initial vertical. Here's our initial horizontal. But now I've added in how far it's falling, which we calculated just with this, where gravity, g, is -10. And believe it or not, this now gives us our coordinates that we have down here. After 2 seconds, we'd be at this. And you're like, wait, where did that come from? Well, we're still 80 meters over, but we're now 20 meters below the 60, which gives us the 40 meters. What's the coordinates at 3 seconds? Hopefully you can figure it out. We would be at 90 in the y direction without gravity. With gravity, we're going to fall 45 meters below that, giving us 120 meters over, 45 meters down. And so here is where these two equations come from. It's a very simple idea that even for non-horizontally launched projectiles, the distance you fall each second is still the same for just as an object with gravity released from rest. So let's try a couple of quick problems. A firefighter standing 20 meters away from a burning building. If the fire hose shoots water at 50 meters per second, angle of 45 degrees, what are the horizontal and vertical components of the water? So this is our 45 degrees. Hopefully you can very quickly do some trig. Sorry, my 45 is bad. And discover that those two sides are 35.4 meters per second. That's both our initial vertical and our initial horizontal. B, at what height on the building will the water hit? Now here's where we actually have to start thinking a little bit. We can use our equations that we just came up with. This is the sort of short version of them. But you'll notice that both these equations involve time. And you might say, well, wait a second, how can we do this? Again, remember, we always make this starting point here, our origin. So where the water's starting out right here, we're making 0, 0. And to solve this, we've got to figure out what time the water is going to hit the building over here. And you might say, wait, I don't know anything about that point. Well, read the question again. The firefighter's standing 20 meters away from the building, which means if we set that as the origin, what do we know? Well, officially we know that by the time the water hits the building, its x-coordinate is going to be 20. We don't know what the y component is, but just based on the fact that we know that x has to be 20 at that instant, we can actually calculate the time. So using the first equation, we can plug in x equals 20. The horizontal velocity or component was this 35.4 times time, and if we solve it, we can figure out the time when the x position is 20 is at 0.566 seconds. And so boom, we've got that. The moment we do that, know that, we can now solve for the y position at that time. Plugging in what we know the initial vertical velocity is 35.4. We've got the time plus 1/2 gravity is -10 times that times squared. And if you solve that, you'll discover that the y position at that particular time is going to be 18.4. And so that's the coordinates of our water when it strikes the building. Here's a challenge problem. I need to warn you on this one. You're like, wait, this is all so easy. Yeah, it gets a little bit more interesting. In this case, the question is, the firefighter shoots water at 50 meters per second and is standing 20 meters away and wishes to hit the fire in the building that's 15 meters above the ground. At what angle must she aim her fire hose? Assume the water leaves the angle or fire hose at 50 meters per second. This time, we have to write everything just in terms of variables. This side is going to be 50 times the sine of theta. I guess I just do sine theta. And the other side is going to be 50 cosine theta. And you're like, oh, we just do it the same way. Well, it gets a little bit more exciting. Why? We don't know the time. And because we don't know theta, this should be cosine. And because we don't know theta, and we can't actually solve for time. You're like, wait, how do we solve this problem? Well, we start out with our basic equations. And in this case, I'm going to write it out the long way, initial velocity. And we can actually plug in the numbers. We want the x position to be 20 when the y position is 15. But we've got two unknowns, theta and time. What do we have here? We have a system of equations, two equations with two unknowns. So you either have to solve one of them for one of the variables and plug it into the other one, which is what I recommend. I'd actually recommend solving this one for time and then plugging into the bomb equation. Or you can graph the two equations with Desmos, or you can use a TI Inspire. And if you do that, you'll actually come up with the answers on this one. Warning, this one is challenging even with the best. Why? Because you'll actually end up with an infinite number of angles. You might say, wait, how can I end up with an infinite number of angles? Well, it turns out you could also get this angle. And a bunch of other angles. We want the smallest angle in the smallest time. And if you do that, you'll discover that's the answer. Programming, you're going to be creating a program that actually launches projectiles. There's a separate video that actually walks you through this one, also linked. Here's a brain break. If you want to try this one, all the answers in this case have the word or the letters HINT in that order. Snooze in a den, cafeteria headwear, Japanese religion, and success, or word for success. I'm going to reveal the answers. If you want to try this on your own, hit pause. But otherwise, I'm going to show the answers in 3, 2, 1. Hibernate, Hairnet, Shintoism, and achievement. That last one was always kind of a challenge. All right. So here's the big idea we've been talking about. For things not launched at horizontal directions, you can just take the path without gravity and then know that it's going to fall the same distance an object would fall from rest after each of these seconds. Sorry, 125 goes off the end of the screen. And that resultant path gives us the path that the ball would take with gravity in this situation. And please forgive my drawing skills as I try to draw both the circles and make a smooth parabola as I'm going. You get the idea. And so here is the conceptual question I want you to think about. Oh, by the way, you'll notice over here I put in very dim terms this. So for projectiles, we don't have to worry about it. But again, if it's accelerating horizontally in any way, we'd have to add this term back in again. Remember, both these equations come from v0t plus 1/2 at squared. We just assume that there's no acceleration in the horizontal. College Board has thrown in situations where there is acceleration that way, and I'll probably show you one later. So here's the question. You've got a cannon here that launches bananas, and you're trying to launch a banana to this monkey that's hanging in the tree. But there's one little twist to this story. The moment you fire your banana cannon, the monkey's going to let go of the tree and begin to free fall. So here is my question, and I want you to think about it. Where should you aim your cannon? Should you aim your cannon below the monkey so that you hit the monkey on the way down? Or, second of all, should you aim your cannon above the monkey because you know the banana is going to fall due to gravity as it flies over? Or, third option, should you simply aim the banana directly at the monkey? Think about this for a brief moment before I talk you through the answer. The correct answer on this one is you need to aim it straight at the monkey. And you're like, wait, how is that even possible? Well, let me take the extreme case. Let's say it takes the banana an entire 1 second to get over there. How far will the banana fall below the path it would have taken without gravity? Well, it's going to fall 5 meters. How far will the monkey fall from rest? Well, also 5 meters, and they'll meet at exactly the same spot. You might say, well, that only works if it takes a second to get over there. Well, if it took 2 seconds to get over there, the banana would fall 20 meters below the path it would have taken, and the monkey will have fallen 20 meters. They'll still meet. You might say, well, it's going to take less than that. If it takes less, just a fraction of a second, the banana is going to fall less than 5 meters, and the monkey is going to fall less than 5 meters, and they'll always meet. The only situation where they wouldn't meet is if you shoot the banana way too slow, and the ground gets in the way before it would meet the monkey. But otherwise, they'll always meet. And you may not believe me on this one, so normally I set up a demo, but if we're not there in person, let me show you this one. Take a look at this. So in this case, if you can see, there's a yellow ball that's representing the banana, and the monkey starts out here at rest and starts falling at the same time. If you can't tell, right here, they hit. You can hear it briefly hit that, and the ball gets deflected towards the table over here. They always hit no matter what speed you set the ball. So we're ready to head into homework. Take a look at this. We've got a metal sphere that is being launched off the end of a ramp. And the end of the ramp is 1.2 meters above the floor. What's the horizontal and vertical components of velocity? So first thing we're going to do on this one, is up here, you just have to do a little bit of trig work. This is 20 degrees. And if you do that, you'll find the two components are this and this. Now, this edge of the ramp is 1.2 meters above the floor. Our question is, how long is it going to take? Well, we actually want to calculate how far away from this it's going to land. Range here just simply means how far away from the end of the ramp is it going to land. It's what you were calculating in your one lab. So solving this one. How do we do it? Well, we actually do know something about the point where it hits the ground. And you might say, wait, how are we supposed to calculate the time that it hits the ground? Well, we know the coordinates of this point. We don't know the x coordinates, that's what we're trying to find, but we do know the y component at this point is negative 1.2 meters. Or the y coordinate, I should say, not component, is going to be negative 1.2. Why? It's now 1.2 meters below the point where it started. So if we use the y equation, and I plugged in negative 10 right there for gravity, we want to figure out when the y position is that. Our initial vertical is this. Where does that come from? Right here. And if you solve that, and by the way, it is a quadratic, so you might need to actually do if you've got a TI-84, go ahead and watch the video where I tell you how to quick program it to solve quadratics. Or you can do negative b plus or minus the square root of b squared minus 4ac all over 2a and solve it that way after you rearrange it. If you do that, you'll discover the time, the positive time, is 0.544 seconds. How does that give us the range? Well, once we know the time of impact now, we can actually figure out what the x position is at that time. Using the x equation, we can plug in the horizontal velocity from up above. Plugging in our time that we just found, we can calculate what the x position is at that time. And boom, you've got it. Hopefully this makes sense. You should be able to do the rest of the worksheet in a very similar manner. Again, just a quick reminder, we always have to find time. Break your velocities, if they're at any angle, into its vertical and horizontal components. And figure out what you know, making sure that you always identify the starting point as the origin, just to make your lives a little bit easier. Good luck, and we will see you soon.